Okay, we should start. So string theory's had some wonderful physics to come out of it, but also some remarkable, incredible spin-offs. And the first speaker today is Carolina Figueiredo, who's going to talk about real-world amplitudes and curves on surfaces.
Yeah, well, thank you so much. I would like to start by thanking the organizers for inviting me. It's a great pleasure to be here. And today I'm going to tell you about a set of results that have been coming out since the beginning of the year. I've worked together with Nima, Song in China, and two of his students, Qi and Jin, that really all come about as a consequence of this new way of formulating amplitudes as a problem about curves on surfaces. So I'm precisely going to start by describing and reviewing this surface integral formalism and contrast it with the standard worldsheet perspective for string amplitudes, and emphasize how the first one is really built around making manifest the behavior around singularities. Then I'll proceed to explain how this different formulation actually gives us access to qualitatively new features about amplitudes, and I'll start with a new pattern of factorizations away from poles, together with some zeros that are associated with them. Then I'll proceed to an interesting kinematic connection between seemingly different theories, trace phi cube theory, the nonlinear sigma model, and Yang-Mills theory. And ultimately, I'll end explaining how this surface formulation offers us a good generalization of kinematics that allows us to define what I'll call perfect integrands for these theories. Okay, so let's start. So the objects that I'll be looking at today are closely related with open bosonic string amplitudes, which at tree level we associate with this picture of a disk, with marked points on the boundaries, the z, the worldsheet coordinates, that are naturally ordered. And from this we get the expression for the amplitude, which is there on the second line. And so the sort of first factor is what's called the Park-Tiller factor, and it encodes the singularity structures that we get when we make the z's collide. The second factor is called the Kober-Nielsen factor, that basically makes manifest the dependence on the momentum of the external states that we're scattering. So when we look at low energies from this object, what we get is this trace phi cube theory, a very simple theory of colored scalars that interact via a cubic interaction, whose amplitudes are extremely simple. So already at tree level, if I fix the ordering of the external particles, I only get contributions from planar diagrams. But so here I have the examples at 4 points and 5 points, and what I would like to highlight is that the momentum that appears in the propagators of this diagram is not any combination of momentum, it's the specific sums of consecutive momentum. So the singularities are located when sums of adjacent momentum go on shell. You see, and if we look back on the left, this fact is not made obvious by the expression that we have. The kinematic dependence does not make the location of the poles manifest. And this is closely related with the fact that in this representation, we need what are called blow-ups to actually access all the singularities. So these are precisely the 2 points that the surface formalism addresses, and the first step in this direction is to think about the kinematics as coming or as being associated to curves on surfaces. So let's look at the example of the disk. If I assign a momentum to each boundary component of the disk associated to the respective particle, then I can define a curve on the disk going from two marked points, C, and to it, I can read off a kinematic variable that I can just read off by homology. So this curve 1, 5, I can deform into this boundary curve whose momentum then is the sum of P1 plus P2 plus P3 plus P4. And note that these are precisely the sort of invariants that naturally appear as singularities. So these XCs are sort of the correct kinematics that perfectly encode the location of the poles. So if we write the amplitude in terms of these XCs, then we make manifest the singularities. So these are the variables that I'm going to be using. And the same story precisely goes through exactly in the same way at loop level. The only difference is that now my surface has punctures or more interesting topology. And so already at one loop, on top of giving momentum to the boundary components, I also need to give momentum to one of these curves that goes from a marked point on a boundary to the puncture, which is associated to the loop momentum. But from the moment that I do this, any other curve that I draw on the surface, I can read off its kinematic variable just by homology. So for example, that curve from 5 to P, x5P, once more I can deform it into a boundary curve and I can read off its momentum. And also at loop level, these curves are precisely in one-to-one correspondent with the propagators appearing in Feynman diagrams, and so writing the amplitude in terms of these variables makes the singularity structure manifest. Okay, so here's an example. Feynman diagrams are then what we get by considering full triangulations of the surface. So at 5 points, tree level, I can get a triangulation of the disk by dividing it into 3 triangles, plunking down 2 curves, x13 and x14. You see there are dual to 2 of the propagators that appear in this particular diagram. And similarly, at one loop, here I have an example of the triangulation that gives us the contribution of the box diagram at 4 points. Okay? So in this language, amplitudes are basically what we get when we sum over all the possible ways of triangulating the surface. So here's a few more examples at 4 points of 2 other diagrams from 2 different triangulations. But the point that I want to emphasize is that when I consider these triangulations, it's crucial that I keep all the curves up to homotopy. Okay? Here's an example where this point's made obvious. So in this case, it's crucial that curve x24 is different than curve x42, so that I get this diagram. Even though in the standard momentum, like their momentum is exactly the same, because they are homologous to each other. So this generalization is going to play a crucial role in a few slides. Okay, so the question that I want to ask is whether we can formulate string amplitudes in a way that instead of points in a worldsheet associated with these z's that encode the momentum of each particle separately, we have an object in which the primary ingredients are precisely these curves on the surface that correctly encode the kinematics that make manifest the location of the poles. And this is precisely the whole point of the surface integral formalism that I'll just quickly summarize for you. So the stars of the show in this formalism are these so-called u variables. There's a u variable associated to each curve on the surface, and it's parametrized in terms of what are called these positive coordinates, y's, that in a moment will serve as integration variables. It's a very simple cross ratios of polynomials in these y's that can be easily derived from a basic counting problem about the curve on the surface that I don't have time to explain. But just in summary, like when I write the amplitude in these variables, it looks like this. So the integration measure is a simple d-log form in the y's, and on top of that I have a product over all the curves that I can draw on the surface of its respective u variable raised to the power of alpha prime times the respective kinematic variable. Okay? And so at tree level, we can actually just go back and connect this formalism with the standard worldsheet one. All that happens is that the Kobe-Nielsen factor gets replaced by this product over the uij to the alpha prime xij, where in this case the u's are really just simple cross ratios in the z's. And you see already here we've succeeded in making manifest the kinematic dependence where the poles are located. And in particular, when we're near a pole, the integral develops a singularity when the respective uij goes to 0. And as for the measure, this first part is just replaced by this d-log form, which automatically blows up all the singularities for you. This is tightly connected with the fact that in this formulation, we don't need to do any gauge fixing anymore. So there's no gauge fixing. And this is also closely connected with the fact that it's trivial to extract the field theory limit. Okay. So at loop level, everything goes exactly in the same way. The formula is exactly the same. The thing is that here, in this product over all the curves on the surface, from the moment that we have a puncture, now there's actually an infinite number of curves that we can draw on the surface, simply because of the fact that we can have curves that self-intersect as they go around the puncture and in an arbitrary number of times. So this product over curves is a genuine infinite product over these self-intersecting curves. And this infinite product is actually crucial so that we're able to reproduce the standard result that we get from bosonic string theory at one loop. Okay? But already here, I would like to point out that if we really only care about what's happening at low energies, and we're just using this object to sort of unify all the diagrams in a single object, we can actually throw away this infinite product and start with something which is much simpler. It's only a product over a finite number of curves on the surface. Of course, this defines a different UV completion, or UV regularization. It's not string theory, but it's given to us naturally by phrasing the amplitudes in this way. We have the flexibility to move around things that are not exactly string theory, but that completely agree at low energies. Okay, so the last point I want to make about this formalism is precisely explain how these u variables make manifest the physical property of factorization near poles. And this just comes as a very simple consequence of a set of non-trivial equations that the u satisfied that I have here, which tells us that a u for a given curve on the surface, if I sum of the product over all the curves on the surface of their u's raised to the power of the number of times that this curve C prime intersects C, then this has to be equal to 1. Okay, these are called the u equations. And we see in the integration domain that we care about the u's, they're all positive. And from these equations, we see that they automatically have to live between 0 and 1, so that the equation is satisfied. Now, about factorization, what happens is that when I go near a pole, my integral develops a singularity precisely in the locus where the respective uij goes to 0. And you see, from these equations, if a given uij goes to 0, then all the ones that correspond to curves that cross ij have to go to 1, so that the equations are satisfied. Okay, this is what's called the binary property of these u variables. And so in the Kolbe-Nielsen factor that our amplitude has, when I go near the locus where a given uij goes to 0, the contributions coming from all the curves that cross it go to 1, so that the product automatically splits into the product of the curves that live exclusively on the left times those that live exclusively on the right, just like we expect. As an interesting historical remark, in the earliest papers by Kolbe and Nielsen, they actually introduced these u variables at tree level. However, they were quickly superseded by the standard worldsheet coordinates, and just in the last few years, these variables were revisited by Nima and collaborators, which provided this positive parametrization in terms of the y's, as well as the generalization to all orders in the topological expansion. Okay, so this takes me to the second part of my talk, which is where I'll explain that this formalism actually lets us conclude new things about the amplitudes. And I'll start with this new pattern of factorizations away from poles that allow us to access also a broad set of zeros for both particle and string amplitudes. So I'll just start by stating what these factorizations are about. So the claim is that if I start with an amplitude and I set a special collection of pi's.pj to 0, crucially I and j should not be adjacent so that I'm not near a pole, then the amplitude factorizes into products of two lower point amplitudes. Okay? And then to get a 0, all that I have to do is further specialize some pi's.pj is one of the factors so that that factor vanishes. So I'm going to call these factorizations splits, just precisely because they're away from poles, and I don't want them to get confused with the standard factorizations that we're used to. So it turns out that these splits really come as a very simple consequence of basic properties of the u variables. They really come about the fact that if I have a subsurface inside a big surface, let's say S1, then I can write the u variables corresponding to curves on this subsurface in terms of the u variables of curves on the big surface. Okay, so let's look at an example. So here's little curve little x inside S1. So this extension formula tells us that the u of this little curve is given by the products over all the possible ways that I can extend little x into a curve on the big surface. So technically what this leads to is I take the product over all the curves on S of their respective u variables, raised to the power of the number of times that little x is contained inside big X. Okay, so this is the feature about u variables. That basically automatically lets us derive these splits just by choosing two subsurfaces such that all the curves that live in the big surface S live in either S1 or S2. Okay, and the minimal way in which we can do this is by picking S1 and S2 such that they overlap precisely in a triangle. So I would like to contrast this with the standard factorization where the two subsurfaces precisely share an edge. See, when they share an edge, then the curve corresponding to the edge does not live in either of the subsurfaces, which was my initial requirement. And so for each of these subsurfaces, I have its surface integral definition in terms of its u variables and the respective kinematics. And now I can literally just use this extension formula that I described to build kinematics under which the amplitude splits. So I start with the product of the amplitudes of the two subsurfaces, and I basically replace in this product their use with the respective extension formula for them in terms of the use of the big surface. So that lands me on an integral over the curves of the big surface, where the exponents of these u's can be read off as simple linear combinations of the kinematics of the subsurfaces. Okay, so it actually turns out that this map follows a very easy graphical interpretation, which tells us that if I draw a curve big X on the big surface that I have there in black, then under these split kinematics, it maps into the sum of the curves it decomposes into. So in this case, big X inside S1 is just X1, and big X inside S2 is just Y2. So you see, precisely because I required that all the curves in the big surface always decompose into at least a curve in one of the subsurfaces, then this means that no x is going to be mapped to 0, making manifest that these factorizations happen away from poles. Okay? And so from splits to 0, all that I need to do is consider a particular split pattern in which one of the subsurfaces is a 4-point factor. Because this 4-point factor, I can actually write the closed form, and I know that the 4-point part will vanish each time that s plus t is equal to 0, more generically, any negative integer. And so following this procedure, we can actually derive a very broad class of zeros that are there for both particle and string amplitudes. together with these split properties, that are both made very manifest and explained by the surface integral formulation and properties about U variables, but for which a standard physical interpretation, maybe in terms of a Lagrangian, these zeros maybe in terms of some symmetries, is still lacking. And it would be very interesting if we could understand this. Okay, so far, these properties I've explained for these surface integrals. They naturally port to trace phi cubed amplitudes in the low energy limit. But a natural question that one can ask is, are there also there for other theories that we care about? And it turns out that both these zeros and these splits away from poles are also there for the nonlinear sigma model, as well as for non-supersymmetric pure Yang-Mills theory. Okay, this should be surprising, and I'll explain this in a second. But it turns out that in the first case, these zeros that we find actually imply the famous zero that we know that pion amplitudes has, which goes by the name of the Adler zero. Okay, so this naturally takes me to the next part of my talk, where I explain an interesting kinematic connection between these three different theories. And so to find this kinematic connection, all that we're going to do is pursue this hint. So experimentally, we observe that there's this broad class of zeros for trace phi cube theory that are also there for the NLSM and for Yang-Mills theory. So we're just going to build the simplest kinematic deformation of trace phi cubed, where I shift its kinematics xij by this linear shift delta ij. And I just require that this shift preserves all the zeros that I found for trace phi cube theory. And it turns out that this lands you on a unique solution. The only linear shift that does this is the one for which delta ij is equal to plus delta if I and j are both even, minus delta if I and j are both odd, and 0 otherwise. Okay? And so if I literally plug this back in my surface integral formula, then I have the standard trace phi cubed part plus this extra term that is raised to the power alpha prime delta. That very interestingly, when I replace the formula of the u's in terms of the y's, highly simplifies to something that looks like just 1 over the product of all the y's. So really the only thing that this shift's doing is changing the measure of integration. Okay? This is how I want you to think about it. And so the claim is that when alpha prime delta is equal to 0 at low energies, I get trace phi cube theory, right? This is what we've been studying so far. But now, if I allow alpha prime delta to have any value that is not an integer, then at low energies, I'm going to get the nonlinear sigma model. And when it finally becomes equal to 1, then at low energies, I'll get pure Yang-Mills theory. Okay? And so you see, because this shift preserves all the zeros, then if I justify this connection, then I know that all these theories have the zeros as well as the split factorizations. Okay, so let's start by looking at this connection for the simplest case, which is the NLSM. So in this case, we can further choose the limit in which alpha prime delta is much smaller than 1, so that we establish the relation directly at the level of the field theory amplitudes. So I start with some field theory trace phi cubed amplitude that has this shift on the kinematics. At 4 points, all that this amounts to is basically shifting the S channel pole with minus delta and the T channel pole with plus delta. And so when I look at low energy, so x is much smaller than delta, you see the leading order in this expansion is precisely the NLSM amplitude. Okay? So this is a very simple example, but just to get a flavor of it. In general, we can actually prove that we're talking about the nonlinear sigma model in 2 ways. So first of all, we can easily show that this object has the correct factorizations. And on top of that, precisely because it inherits all the zeros that we found for trace phi cube theory, in this case, these actually imply the Adler zero. And at tree level, these 2 features are enough to be able to argue that it has to be the NLSM. At general loops, we really have a Lagrangian derivation of this connection that explains why this shift works. I would like to end this part just with a practical comment that this connection is extremely useful because the nonlinear sigma model Lagrangian is an infinite Lagrangian, so computing its amplitudes at high points becomes complicated, while the trace phi cubed one is extremely simple. So we can use this connection to then efficiently compute nonlinear sigma model amplitudes as well. Okay, so now let's proceed to the limiting case where alpha prime delta is equal to 1, for which I should get Yang-Mills theory at low energies. And so really here, all that happens is that the measure goes from a dy over y to a dy over y squared form. And so the first thing one can ask is, if I'm talking about gluons, the polarizations should appear at some place. And it turns out that this object, what's really describing, is describing the scattering of colored scalars, but they're crucially coupled to gluons in the standard way. And so this means that if I start with a 2n scattering of these scalars that is given by this form, as I'm claiming, then I can extract n residues where basically I make each pair of scalars fuse into a gluon, and by taking these residues in this object, I can just land on the gluon amplitude. Okay? So this is how we're formulating our gluons, via these scaffolding scalars. That's what we call them. Okay, so it turns out that at tree level, we can really sort of establish a connection between our formula and the standard bosonic string formula for gluons. So this is just very schematic, but if you start with the standard tree level form for the scattering of gluons, you have this extra exponential part that encodes the polarizations, and all that you need to do is pick a limit where you fix the polarizations of the gluons to live in higher dimensions, so that effectively they become scalars in the lower dimensions. So they become scalars, so you're now describing the scattering of these scalars, and that highly simplifies your expression to a single term, which is precisely the term that I started with when written in terms of these u variables and the y's. So this is what we can see at tree level. At loop level, making the connection like this would be extremely more complicated, so all that we do is we start with this trace phi cubed form that we know before, and then we change the measure from a dy over y to the dy over y squared. And this is what defines for us what in a second I'll call the surface gluon integrands. But for now, I just want to say that this formulation of gluon amplitudes is completely dimension agnostic. The dimensionality enters as a parameter. And on top of that, precisely because the surface integral formalism let us access the singularities in a very simple way, one sort of objects that we can get from it very efficiently is what are called leading singularities, which is what you get from a given diagram when you put all the internal propagators on shell. And this allows us to perform very non-trivial checks on this object. Okay, so this takes me to the last part of my talk, which is precisely at loop level. I'll explain how the sort of surface defines a generalization of kinematics that allows us to determine what I'll call perfect integrands for these two theories. Okay? So it's been a long-standing challenge to determine amplitudes of real-world theories, or even in general, like integrands, just by knowing what happens on single cuts. With this, I mean just by knowing what happens when a single internal propagator goes on shell. So at tree level, this has had massive success. All that we need to know is that the amplitude is a rational function, and on top of that, near a single pole, it factorizes into lower point amplitudes. And using these two facts, we can just recursively construct the amplitude, famously using the BCFW recursion relations. However, already at tree level, it's crucially that we go a little bit away from the standard notion of momentum by extending from Lorentzian kinematics to complex kinematics. This is just because the sort of starting building block of this recursion, the 3-point amplitudes, vanish in Lorentzian kinematics. But if you try to do the same thing at loop level, it's actually impossible. And the main reason is that already at one loop, you have this new sort of single cut, where you cut the loop propagator open, and you would like to match this object with what you get from the tree level, where you glue two adjacent legs. But however, on the right-hand side, we have a contribution from a diagram where these two propagators meet. And because of momentum conservation, we get this 1 over 0. So this is what's called the forward limit, and it's divergent. It's not divergent in the case of maximal supersymmetry, because when we sum over the supermultiplet, this contribution actually cancels. But for the theories that we're describing, it is usually divergent. And this is associated with the fact that there's no d-integrand for these theories. With this, I mean an object that matches on all the cuts, which is also closely related with the fact that there's no integrand for pions that has the Adler zero directly before loop integration, and an integrand for gluons, which is directly gauge invariant. So let me just rephrase this problem in terms of the surface. So all that's happening is that I'm literally going on a cut where I cut through one of these curves that joins the mark point on the boundary to the punctures, cutting it open into a tree. And the problem is that this x11 curve, when I read off its momentum by homology, it has to be evaluated to 0. Right? That's what's causing the divergence on the right-hand side. However, from the surface integral perspective, we have the flexibility of really giving names to all these curves, even if they don't have a standard meaning in momentum space. So we can basically give names to the tadpoles as well as to external bubbles for which a similar issue arises. So basically, really like generalizing kinematics away from like this homology idea to really homotopy. And in this way, we have an object which is regular in all these limits that satisfies all the cuts. Okay? So we already saw that at tree level, we had to go from Lorentzian kinematics to complex kinematics. Now at loop level, we see that we have to go from this complex to what I'm calling surface kinematics, which is really think of the kinematic invariance as curves on surfaces. And by doing this, allows us to define these surface integrands for these two theories, which we can then compute recursively. So we've done this explicitly at tree level as well as one loop. For gluons, we're still working in the higher loop case, and for pions, this has been done at all orders. And on top of that, these objects also have directly at the level of the integrand, so before loop integration, the Adler zero in the case of pions, and gauge invariance for the case of gluons. And just as a last quick comment, precisely because I have the connection between these theories and this trace phi cube theory, all the split properties that I arrived for the first one are also there for these other theories, and allow us in this case to make statements about multi-soft limits at all orders. Okay, so this brings me to the end. Well, I'm just going to end with some quick future directions. Of course, if we want to describe the real world, we should learn how to do fermions in this way, and more broadly speaking, get closer to the realistic particle content of the standard model. But all that I've told you today is really about colored theories. That's extremely important. Well, gravity is uncolored, so if we want to find a way of doing this, the problem would now be something about closed curves on the surface rather than open curves, as these ones are the ones that correctly encode the kinematic dependence. Okay, that's all.
Are there any questions? Please.
So in the case of the ABHY associahedron,
Yes?
that integral has an interpretation as the volume if you write that in terms of the dual variables. Is there anything similar for these surface integrals?
Yeah, it's actually no, because precisely, you see, to be able to give it a standard, in the ABHY case, it's crucial that you have this canonical form, which is really associated with the fact that your measure of integration is a dy over y. From the moment you change it to a dy over y squared, now it's like when you take the low energy limit, you don't land on something that has a similar interpretation. So it's not clear whether there's a polytope in that same sense.
David.
So given that, in open string amplitudes, you can recover closed string amplitudes.
Yeah, so I mean,
You should be able to recover.
you can do. I mean, if you do double copy at tree level, that definitely works to get you can even get this sort of scalar scaffolded gravity in this way, where the gravitons come from parascalars. But this sort of thing that I was mentioning in the end is really that there should maybe be a more sort of intrinsic uncolored way of talking about it, rather than this double copy like way.
Uncolored way.
Yeah, uncolored way, exactly. Sort of which really is tuned about these like closed curves on the surface.
Which doesn't yet exist.
Which doesn't yet exist. No. That's kind of a future direction, yes.
By the way,
Another question.
Historically, the U variables were introduced long before Kolbe-Nielsen. They were used from the beginning to generalize the Veneziano amplitude.
Oh, I see.
And in fact, Fubini and Veneziano proved factorization of the dual resonance model using the U variables.
I see. Okay. I didn't know that. Thank you.
This question over there.
Hi. Could you elaborate on the difficulties for the gravity case?
Yeah, well, we haven't tried. So, I mean, there's a few technical difficulties that I don't want to get into much detail associated with the fact that, I mean, you can already access the graviton pole in the open string case, right? Starting from the annulus. I mean, you should have the sort of graviton emission coming from there. And it looks like the sort of singularities that you have occupy a loci. This is really the technical terms. I mean, when you want to extract these singularities, you sort of have to access them in a special way that we still don't know very well how to do. This is one of it. I mean, you can definitely do double copy. I don't think there's any problem in doing it that way. I'm just saying that if you want to do it in this more intrinsic, uncolored way, we still don't know.
The back.
Could these sort of techniques be useful in calculating some of these higher genus, higher derivative corrections to the string amplitudes that are currently unknown? Like using double copy or using one of these methods by which you could reduce it to the open string?
You mean to sort of reduce them or exclude some of them? Is that what you're saying?
I mean, it's like, do these actually do you have enough already to constrain the actual numerical value of some of these higher derivative corrections that are unknown?
Yeah, not that I don't think so. I mean, you could ask for one thing that you could ask if you think that, for example, these zeros and these splits that I mentioned are really like physical, then you could say, okay, I'm only going to allow higher derivative corrections that have these properties. And it's going to definitely restrict what is the higher derivative corrections that you get. But I think this is the most closer to that.
Are there any other questions?
Sorry, could you comment what happens to these zeros as you include, say, loop corrections? Because if we have zeros for quantum amplitudes, they are resonances, right?
Yes.
So they have a very clear physical interpretation. So what happens as you start including quantum corrections?
Yeah, so if you go to one loop, you can actually still access these, you can have these zeros be statements post-loop integration, which, I mean, they're definitely there at the level of the integrand, but sometimes they involve fixing the loop momentum, so it's not very interesting. But you can actually make them statements post-loop integration, but for that, you need to go these soft limits. So basically, you need to set some particles soft so that the loop momentum dependence decouples on the split factorization, so that one factor depends on the loop momentum, the other one does not, and then you can actually derive zeros at all orders. I don't know if this answers your question.
Okay, thanks.
David wants to ask a quick follow-up. We're almost out of time, so please make it quick, David.
No, just an idea that occurred to me. I wonder, tell me if it makes any sense. So Adler zeros, of course, are a consequence of spontaneous symmetry breaking, of kernel symmetry. You said there's no... So what about the following stupid conjecture? That the zeros are a consequence of spontaneous symmetry breaking in string theory of some underlying symmetry of string theory, which we still don't understand.
Yeah, that's totally possible, because they're actually there at the level of the full string amplitudes, more primitively. So that's possible. We just, we don't have an answer to that, but that's definitely possible.
Okay, I think we should call it a day there. Thank you. And let's thank Carolina again.
Thank you.